Hello students, this is another lecture on electromagnetic induction. Today we're going to discuss the questions, previous year's questions based on mutual inductance, which was asked in AHSEC final examination under Assam Higher Secondary Education Council. Okay, so before we start, please do subscribe the channel, hit the thumbs up button, also share with your friends, inspire me to create new contents for you and help me to grow my channel. And if you want to follow me on Insta, this is my Insta ID OJHALAKHYAJIT123. That's my Insta ID. You can follow me on Insta. So now let's see. So here you see, first question, what is the mutual inductance? And we have two coils S1 and S2 are two long coaxial coils. That means this is one coil, suppose, and another coil is coaxial, which is inside it. You can consider that way, and axis of these two are same. Okay, so let me show you. This is one coil, suppose, right, like this. We have one coil and another coil inside it. Okay, another coil inside it. So hope you can understand this. I will explain it. Then radii of the two coils are R1 and R2, and R1 is less than R2. Okay, R1 is very less than R2. So the coils are taken as S1 and S2 and of radii R1 and R2 respectively. So there were two coils. This is one coil and another coil inside it. Okay, so the inner coil is suppose S1 and the outer coil is suppose S2, and radius of the inner coil must be R1 because R1 is less than R2. Okay, so we need to find the expression for mutual inductance M12 of S1 with respect to S2. So now let me explain how to do this. So let me tell you, this was asked in AHSEC final examination in the year 2022. Okay, so this is very important for 2026. Okay, so now let's start. First, let me explain what is mutual inductance, as it was asked in this question. What is mutual inductance? So here you see, suppose we have two coils. Suppose we have two circuits. This is one circuit. Okay, and current passing through this circuit is suppose I, and another circuit here which is very close to this. Okay, and current is passing through this circuit only, I, and the magnetic field produced due to this current in this circuit will pass through the circuit which is close to it. Okay, and then flux through this circuit, flux through this area bounded by this circuit will be directly proportional to this current in the first circuit. Okay, so phi is directly proportional to I, and if we write equal, then we need a constant. That constant is nothing but mutual inductance. Okay, so hope you have understood this. So you can say this is nothing but the ratio between the flux and the current, right? Hope you have understood this. That means ratio of flux through the secondary coil with respect to the you can say that ratio of flux to the through the area bounded by the secondary coil to the current in the primary coil. You can say that way as well. So now, what is the second part of the question? Let's come to this part of this question. Here you see, let me take a new slide. So here you see, here is the diagram. Okay, so we have two coils here of same length L. Okay, and the two coils are S1 and S2, and their radii are respectively R1 and R2. Here you can see R1 is the inner coil, radius of inner coil, and R2 is the radius of the outer coil. Okay, this radius is R2 and this radius of inner one is R1. Okay, we have considered that way. So now let me write what we have taken here. Okay, so actually it is mentioned in the question. Okay, so S1 and S2 are two coaxial solenoid. Okay, so here you see, it is given that S1 and S2 are two long coaxial solenoids of radii R1 and R2, and where r1 is very less than r2, okay, respectively, of length l. Okay, number of turns in S1 we have taken capital N1, and number of turns in S2 is capital N2, and number of turns per unit length in S1 will be total number of turns by length, that is small n1 is equal to capital N1 by L. Similarly, in S2 we're gonna get N2 is equal to capital N2 by L, right? So this implies that capital N1 is equal to small n1 into L, and this implies capital N2 is equal to small n2 into L. That's what we can have, right? So hope you have understood this. Now you see magnetic flux link with S1, this inner solenoid, magnetic flux link with the inner solenoid, okay, due to the S1 current in S2. That means magnetic flux link with the S1, which is the inner solenoid, due to the current in S2, due to the current I2 in S2. So I have taken that current in S2 is I2. Okay, here, hope you have understood this. So here we're going to write, therefore magnetic flux linked with S1 due to the magnetic field produced by the current I2 in the coil S2, that is given by, so flux link with S1. So if we consider flux link with its coil is its turn with in S1 is phi 1, then number of turns in S1 is N1. So that flux link with S1 we can say N1 into phi 1, and that's gonna be equal to, if the mutual inductance is M12, then it will be given by M12 into I2. I will explain why. This is suppose equation number 1, where this M12 is mutual inductance of S1 with respect to S2. As I have already explained in definition of mutual inductance, suppose we have two coils, this one and this one. If current flows through this and the magnetic field passes through the coil which is close to it, and if the flux through this coil in the secondary coil is phi, then that will be proportional to I, which is the current in the primary coil. So that's why here we have got, this is the flux in the secondary coil in the S1 due to the current in S2, okay, and these two should be proportional. And here in case of a single turn we used to write phi. If we have n number of turns, we used to multiply capital N here, the number of turns, okay. So here we have proportional to this current, okay, and if you write equal sign, then we need this constant M12, which is the mutual inductance of S1 with respect to S2. Now let me copy this equation number 1 and let me take the new slide. Okay, let me take a new slide. So here is the equation number 1. Okay, so now you see, this is the outer coil S2 suppose, and inner solenoid is S1. This one is the inner solenoid, okay, S1. Now you see magnetic field due to this S2 or this outer solenoid, magnetic field due to current I2 in S2 is given by, this is mu naught N2 I2, okay. So this is magnetic field inside a solenoid is given by this expression. Just to remember it for the time being, okay. So hope you know this formula, okay. I have considered that this is known to you, okay. The magnetic field inside a solenoid is mu naught N2 I2 if the current is I2 through the circuit, through the coil, and N2 is the number of turns per unit length. And then you see, we know that flux is equal to magnetic field into area, right? We know that. So in that case, so that's why N1 phi 1 can be written as, therefore N1 phi 1 can be written as we have got magnetic field is this. So magnetic field mu naught N2 into I2, and then area will be given by we have to take the, as we are calculating the flux through this inner solenoid. This is the solenoid with small radius, so we're going to take the cross section of this S1, okay, which is inside the which is the inner solenoid, okay. So its radius is R1, so we're going to take pi R1 square. This is the area, and you see we have total number of turns in S1 is N1 is equal to N1 into L, N1 into L, as I have already given here. This is this one N1 into L. So this is the flux through one turn only. For total number of turns, we need to multiply that total number of turns, that is N1, which is nothing but N1 into L, right? N1 into L. So now you see, okay, if we use this in equation number 1, this is suppose equation number 2. So from 1 and 2, from 1 and 2, what we're gonna have? We're gonna have first, let me write the right hand side of the equation number 1, this one, that will be equal to the right hand side of the equation number 2, because their left hand sides are same, right? If these two are equal, then these two must be equal, right? Hope you have understood this. So that's what we're gonna have. So from here, you see this I2 cancels, so we're gonna get the required expression which we need. So that is M12 is equal to mu naught N1 N2 pi R1 square, then into L, okay. So this is the required expression, okay. This is the required expression for mutual inductance of S1 with respect to S2. That is what we needed to find, right? So hope you have understood this. Here this mu naught is nothing but permeability of free space, right? This mu naught I am writing here is mu naught is permeability of free space, right? So now let me take the next question. Here you see this was also asked in 2022, okay. So two concentric coils, radii of the two coils R1 and R2, radius of inner coil is R1 and outer coil is R2. I will explain it in the new slide, okay. So we need to again find the expression for mutual inductance as we did in the last question. Here R1 is very, very less than R2, okay. R1 is very, very less than R2, okay. We need to find the mu12, that means mutual inductance of this is coil 1, suppose inner coil is coil 1 and outer is coil 2. So we need to find the mutual inductance of coil 1 with respect to coil 2. So now let me take a new slide to explain this, okay. Suppose we have two coils, this is one and another inside it, okay. So radius of this inner coil is R1 and that of outer coil is R2. So R1 is very, very less than R2, right? We have taken that way, okay. So first you need to mention this, that two concentric coils having radii R1 and R2 are placed coaxially as shown in the figure, okay, where R1 is very, very less than R2, okay. So let me consider that current through this outer coil is suppose I2, okay. I2 is the current in the outer coil, okay. So now you see, if phi is the let me write here phi 12 or phi simply 1 is the flux through the inner coil due to the magnetic field produced by the current I2 in the outer coil, then we can say that phi 1, this phi 1 2 or phi, let me write phi 1 is proportional to I2, and to write equal, we need the mutual inductance. We need a constant that is called mutual inductance M1 2, so which represents the mutual inductance. M1 2 is the mutual inductance of inner coil. So let me take this is C1 and this is C2. Inner coil C1 with respect to the outer coil C2, okay. So here M1 2, that's gonna be equal to or let me keep it this way, simply keep it this, let me keep it this way. This is suppose equation number 1. Let me take a new slide and let me copy this as well, this equation number 1. Here is the equation number 1. Now you see, so phi 1 2 is the flux through the coil 1, inner coil, flux through the inner coil, area bounded by the inner coil due to the magnetic field produced by this outer coil. So magnetic field at the center of a coil, we know that formula is magnetic field produced by a coil at the center is given by mu naught I by twice of its radius. If we have n number of turns in its coil, then we have to multiply n here, okay. So here we're gonna write B2 is the magnetic field produced by the coil 2, and it has suppose n2 number of turns, and radius is R2, right? Radius is R2. So now you see, let me mention n was n1. So here let me tell you one more thing, okay, that is if we have n1 number of turns in coil 1 C1, then here we need to multiply n1, okay. So let me go back to the previous slide. Here we should have n1, okay. Now n2 is the suppose number of turns in coil 2 C2, okay, in coil C2. Then magnetic field at the center of coil 2 C2 is the coil 2, at the center of coil 2 will be given by B2 is equal to mu naught, that is permeability of free space, N2 current through the coil 2 is C2, coil C2 is I2, current through the coil C2 is I2 divided by twice of its radius, that is R2, okay. Hope you have understood this. And so we need to find the flux through this inner coil. So if the radius of the inner coil is R1, if the radius of the inner coil is R1, so its area of cross section is pi R1 square, and we know magnetic flux, therefore flux through the inner coil C1, that will be given by N1 phi 1, that's gonna be equal to magnetic field B2 into area, that is pi R1 square, because we are going to find a flux due to the magnetic field produced by the outer coil through the inner coil. That's why area of cross section is taken, area of the inner coil actually, and magnetic field is taken at the center of the outer coil due to the outer coil, right? Hope you have understood this. Now B2 we have got that mu naught N2 I2 divided by twice R2, and here we have pi R1 square. Okay, so hope you have understood this. Okay, and okay, now let me write the final result. So this is suppose equation number 2. From 1 and 2, what we will get? Let me copy equation number 1 and equation number 2. Let me take a new slide. This is equation number 1, and let me copy the equation number 2 as well. Here is the equation number 2. Here is the equation number 2. So from 1 and 2, from 1 and equation number 2, what we will get? We will get that mu 1 2 I2 is equal to mu naught N2 I2 by twice R2 by R1 square. That's what we're gonna have, right? Let me add one more thing. So here you see, as in inner coil we have N1 number of turns, so we need to multiply N1 also here. Okay, I forgot to multiply that. Here we should have N1. Okay, if we get N1 there, then the final expression will be like this. Here it is N1. So therefore here you see this I2 cancels, so therefore we're gonna have, therefore M12 is equal to mu naught R1 square. I forgot to write the pi as well as pi R1 square N1 into N2 divided by twice R2. So this is the required expression. So this is the required expression. This is the expression for mutual inductance of inner coil with respect to the outer coil, right? So hope you have understood this. Thank you for watching. See you in the next question. We have numerical problems as well, which were asked in previous year's exams from this chapter. So those will be solved in the next video. So stay connected. Thank you for watching. See you in the next video. Bye bye.